right, so now we have Sebastien Reneaux-Petel from IAP and CNRS, and he's going to talk about primordial futures, probing primordial futures with the stochastic gravitational wave background. It's a pleasure to have you here. Thank you very much. That's
all right. You can hear me well? Okay. Well, thanks to the organizers for this very nice workshop. Thanks for the opportunity to give this talk. So I talk about a bunch of works in the last year and some to appear, in particular in collaboration with excellent postdocs with me at IAP, Jacopo Fumagalli and Lucas Witkowski, and other collaborators, Guillaume Domenech, Mauro Pieroni, Gonzalo Palma, Spiros Tsipsas, and Cristobal Zenten. Oops. Okay. So we're talking about new physics, and indeed there are plenty of reasons to have new physics from what one can call the cosmological dark ages. So here, this is basically the numbers of e-folds of expansion of the universe, and we're here. And basically, seen that way, we know very little about the universe. We know basically the last 20 e-folds, starting from BBN. And we have an observational window on the largest scales that existed the Hubble radius during inflation, during a limited amount of 10 e-folds. We have basically no idea of what's going on in the remaining, let's say, 50 e-folds of inflation and afterwards. So this has been studied a lot. Well, see the previous talk with reheating, phase transitions, etc. Today I will talk about these dark ages of inflation itself, and in particular about primordial features. So we will learn new things about inflation with stochastic, with a stochastic gravitational wave background, which can have very interesting properties of different type. There can be the frequency profile, so omega GW is a function of frequency. Frequency or K will be used in the same manner in this talk. They are just related. In general, also the plus and cross polarization state need not be the same, in which case the gravitational wave background is chiral. There can also be anisotropies. Strictly speaking, this is just the monopole, but just like the CMB, omega GW at some point will be measured with anisotropies, and there will be science in it, which can be correlated with other probes like the CMB and so on. And well, I didn't put reference, but with my group, we organized a workshop some time ago about this subject where you can see lots of references. So in this talk, I will talk about indeed the frequency profile of omega GW. And I want to show you that there are lots of motivated physics of inflation that give rise to oscillations in this frequency profile. So most frequency profile that have been studied before are smooth, let's say a bump or power law or broken power law. What I'm talking about today is hopefully one day we will have some detectors, LISA, the LISIGO, Einstein telescope. This is rather irrelevant for the discussion now, with some detection and with some wiggles. And I want to motivate them and show that there is some nice physics in it. So that we're all on the same page. Inflation. What does it do? It takes a tiny patch of space and it stretches it to become the entire observable universe during a small amount of time at an almost constant Hubble rate. And during that time, unavoidable quantum fluctuations get also stretched to provide the seeds for all, to provide the primordial fluctuations, the seed of all the structures in the universe later on. All right. So, as you all know here, we have the wonderful Planck data that are in agreement with the simplest models of inflation, single field slow roll. But an important point for all the rest of the talk is that nobody believes that these models are more than toy models. As theoretical physicists, we are not happy with just invoking a single scalar field, decoupled from the rest of physics, decoupled to the standard model. We want to know much more. We want to know what is this inflaton, where does its potential come from, in which extension of the standard model does it belong to, what was the energy scale of inflation, how did it transfer its energy to the standard model degrees of freedom? Was the universe so simple as to have just one degree of freedom or not? If not, what was the coupling of the inflaton to these other fields? These are the kind of questions that people in inflationary inflation ask themselves. And so if you take all that seriously, let me remind you of one of the way to realize the difficulties of inflation is the so-called eta problem. Think about the simplest things, single field slow roll. Try to make that work. This requires, as you know, a very flat potential with first and second derivative, very small compared to the Planck mass. That's this parameter eta that measures the acceleration of the scalar field. In practice, this is a measure of the mass of the inflaton in units of the Hubble scale, the characteristic energy scale during inflation. And so this has to be much smaller than 1. And that's a natural, naturally, in quantum field theory, you expect the mass of your scalar field to be of the order of your cutoff of your theory, which would be much greater than h. So you expect steep potentials, and inflation requires you exactly the opposite. Another way to see that, which is quite similar, that's formulated slightly differently, is take what you think is your slow roll action and look at higher order corrections suppressed by a very high energy scale, m, the cutoff of your theory. Even if m is pushed to the Planck mass, this will generate corrections to eta, which you want to be small, of order unity. So basically, the Planck scale physics does not decouple, and everything is terribly complicated. So the simplest hope, if you're a model builder, is to invoke a single scalar field with a very flat potential. And if you want to embed inflation in high energy physics, you find, let's say, in string theory, which somehow you have to, if you want to take these problems into account seriously, because you are sensitive to Planck scale physics, you find many degrees of freedom, steep potentials, large couplings, not at all what you want. So taking that into account, single field slow roll, which seems to fit the data, is at best an emergent approximate description. And people for decades now have developed tools to look for deviations to that. And we in cosmologists look for deviations to this in a motivated manner, basically, very roughly speaking, in 2 forms: primordial non-Gaussianities, 3-point, 4-point functions, and primordial features. And okay, I want to talk about that today. Primordial features, I take that to mean in general oscillations in contradiction to a smooth, let's say, power law in correlation functions, 2 points, 3 points. So I mean, these 2 things are not completely decoupled. There can be features with non-Gaussianities, and there's a lot of information in it. And features has been studied enormously for the CMB large scale structure, 21 centimeter. And I want to show you that there is also interesting physics about features and gravitational waves. So there are 2 main types of features that are motivated by different inflationary mechanisms. Sharp features and resonant features. Describe them briefly. Sharp feature means is the name basically of as well the power spectrum and the mechanism that give rise to it. Think of anything that breaks the adiabatic evolution of slow roll during some time. It can be a step in the potential, a turn in field space. It can be in a wide variety of ways. In practice, the end result will always be the same. The power spectrum will have a given envelope, and this envelope will be modulated by oscillations, which are periodic in K, with a frequency that is related to the time of the relevant feature during inflection. Other mechanisms I will not describe right now, but experts will recognize, will give you oscillations as well, but which are now periodic in log of K. So with this omega log here, which is dimensionless, which is related typically to the frequency of some oscillation in the background. All right, so that was, let's say, the usual motivations for looking for features on large scales. But now I want to look at other type of features on small scales. In particular, so on this 10 EFL that we have access to, slow roll, despite the fact that it's soy model, seems to fit the data. And okay, we're looking for corrections to that. So small wiggles or small non-Gaussianities. But we have very few, basically almost no constraints on small scales. And what I want to entertain today is the possibility that the physics is very different. For example, that the power spectrum has a large bump here. And actually, I can argue that this thing, which looks like, okay, inflationary people do model building, put what they want as usual to have a feature and so on, is actually natural. Because what I told you, and so this thing that can be seen as an unnatural is actually natural. Because precisely, remember the ETA problem. People have been working for 40 years to construct with difficulties realistic models of inflation, because it's actually hard to have a prolonged stave of slow roll inflation of 60 e-folds uninterrupted. What is actually natural is to have steep potentials. In that case, you just inflate for 5 or 10 e-folds in some direction in the landscape, and then you bifurcate into another one because you find the new flat direction and so on and so forth. That's actually what is natural.
But what you really want is a part that is flat and a part that has this feature, right?
So
you are introducing a scale, so it's hard to keep the other part flat when you actually build a model.
It can be. I mean, you can, let's say, here is just one example, but if you imagine, for example, that, okay, we were lucky and inflation, the inflaton found a flat direction during 10 e-folds that we observed, and then it bifurcates into another direction, then another one. It doesn't need to be like that. It can be, let's say, a boost and then a plateau, simply because inflation was occurring with different properties.
Yeah, an actual particle physics model, I'll understand better. Thanks.
Okay. So, and indeed, this type of things has attracted quite some attention recently, especially if you want, even phenomenologically, to generate primordial black holes, because you know that we have hints of, let's say, depending on taste, but I mean, we may already have detected primordial black holes. But this talk is independent of that. But these kind of things have been studied also in this context. But independently of whether such kind of physics can generate PBH, these leave a signature in the stochastic gravitational wave background. And actually, what I want to explain as well is that when you have such a peak, it's actually often associated with oscillations. That actually, this peak is just the envelope of your power spectrum, but you have oscillations superimposed in it. So really a feature, but not a feature that is small, a feature that is an entire part of the signal. So this I want to explain in a bit more detail, slightly more technically. What is a sharp feature? It's basically, here is time Young inflation in terms of number of e-folds, or equivalently, you can talk about the scale K feature that crossover radius at that time, before its standard Bunch-Davis. Something happens. I don't have to say what. A step in the potential, a turn in field space. The general consequence is afterwards, you are in an excited state. That is, your mode function is not anymore the one of Bunch-Davis, but it's basically this one, which have positive frequency modes plus negative frequency modes with some so-called Bogolubov coefficients alpha and beta. Beta equals 0 is the usual one, and with alpha equal 1. The quantization of your theory relates this thing with these constraints. So usually beta equals 0, alpha and 1 gives you that. And indeed, these are excited state with a non-zero occupation number and related to non-zero values of beta. You can, now that this excited state has been created, so let me just be clear that this excited state that I will consider, I do not consider things like alpha vacua that have been there forever. I consider that they are dynamically generated by something, okay, by this sharp feature. What is important when you do this, let's say, matching, is that actually the phase of the Bogolubov coefficients here and there are related in a very precise way and select, let's say, the time or the scale of the feature. K feature, again, is basically corresponds to the time here. And you can compute the power spectrum. It's basically just the mod square of alpha plus beta. And if you forget about the mild K dependence of alpha and beta and concentrate on that, you find this cost factor. So I put that in a slightly different form. I just schematically factor out by alpha, and I have this. So this is really of the schematic form of the sharp feature that I was mentioning. There is an overall envelope that depends on K that can be boosted around some scale. And this is, and you have a cosine oscillations that modulate that with some given amplitude. And again, the frequency is related to the scale somehow of the feature.
What this sharp feature is. I understand you want to be kind of generic about it, but what exactly is happening in the potential that gives you a sharp feature?
Okay, it doesn't have to be the potential, but if you think about, let's say, single field model, think about a potential that is slow roll and then has a step. during that time, you will break the standard slow evolution, and that's a typical example of a sharp feature. Or in multi-field inflation, you inflate in one direction, and then you turn because of the interplay between the potential and so on. That's typically this kind of stuff.
I think that what we're worried about is that if you insert such a feature, it amounts to adding a scale in the potential, which is coupled to the flat part in some sense. So I mean, I think if you write in practice, it's hard for it to be technically natural. So
sorry.
So worried that this scale, so this sharp feature that you're injecting, is normalize the flat part.
I understand.
I'm guessing we want to see.
I understand. Then if you go to model building, maybe, for example, a multi-field inflation that I have in mind will offer more flexibility than single field, because in that case, maybe the feature can modify things on large scales. This I understand. I will show you some concrete models, but because things are very generic, I want to emphasize that. So what is the consequence of that? So because of the quantization, these things are related. Beta over alpha can be maximum of order 1. So bunch Davis is 0, very large particle production is this of order 1. So again, when this ratio, beta over alpha, is small, that corresponds to 1 plus small. So that corresponds to the standard small wiggle that people have been looking for in the CMB and the Alaska structure. What I'm looking at today is actually when beta over alpha is actually of order 1. In that case, it's really basically, you see, order 1 oscillations, 1 plus 1 times the cos. In addition to that, the signal is boosted by itself. And that's really an important point. Actually, as I told you, if you consider a boosted power spectrum, a power spectrum that around some scale is much larger than the naive value P naught, it means actually just from that this alpha is much greater than 1. But if alpha is much greater than 1, beta also has to be, so that the ratio is of order 1. And if the ratio is order 1, you have basically order 1 oscillations in the power spectrum. So that if you have a large peak, very much considered in all models generated, for example, primordial black holes, from a localized event, from a sharp feature, this will necessarily have order 1 oscillations in it, like in the sketch that I was showing to you. That's quite generic. That's why I think it's quite interesting. Then, okay, we have some explicit realization of that I don't want to go into the detail, but the type of models that we've been considering is a sharp turn in field space. So if you have multiple inflationary fields, you can change the direction of your inflaton. And this is not very important for the rest of the talk, but this can be quantified in terms of, okay, how sharp is the turn? What is the duration of that in terms of number of e-folds? When does it happen? What is the corresponding scale? And most importantly, what is the rate of turn? And this parameter, eta perpendicular, eta, because it's actually still an acceleration, but it's an acceleration perpendicular to the trajectory, can be large and in these scenarios. Tells you how strong the turn is. And I don't want to show you all, to explain to you all the equations and all the details, but really, if you actually solve in this kind of models the dynamics, you actually find that around the scale of the feature, the power spectrum, which may well be 10 to the -9 here on CMB scales, is boosted by orders of magnitude, 4, 5, 6 orders of magnitude, and comes back to standard values, with, in addition, these rapid order 1 oscillations. This is computed for I mean, let's say, from first principles, numerically and analytically, as you can see here. But that's just an example. It's actually, okay, the question was, can I show the potential? Actually, we phrase that in a model-independent manner in the effective field theory of inflation. So you can cook up models that give rise to that, but we prefer to actually present things in model independently, but I can show you later. So of course, you cannot do what you want. You cannot just say, oh, I boost the primordial power spectrum by several orders of magnitude theoretically, and do as if nothing happened. There are strong theoretical constraints. Because you have an excited state, these particles carry some energy, and so in general, they can back react on the background. And if you don't take that into account, you have, okay, there is some bound. Also, of course, because you excite mode on suborbital scales, you have to be careful about theoretical control. And so in this theory, basically, it's not enough that the power spectrum should be much less than 1, which you can naively sort is is the correct criterion, it's actually the thing that should be much less than 1 is this times this large number. Remember, there's this eta perpendicular parameter, but you can think of it model independently, is a large parameter that quantifies the strongness, let's say, of the feature. So this is just to tell you, okay, we are aware that we cannot do what one wants with this kind of things, and we took that into account. Yes.
Mentioned that you do some EFTF inflation to characterize the properties of zeta, but I think typically people assume some shift symmetry so that they can do derivative expansion in the EFTF inflation. But then if you have these big bumps in zeta.
But I mean, the EFTF, an effective field theory of inflation doesn't have to be the effective field theory of single field inflationary fluctuations with a shift symmetry. Okay, this is just one corner of it. I can explain you later what if you will consider generic multi-field degrees of freedom, you can also consider, you can also formulate that in an effective field theory manner with zeta or pi, the Goldstone boson of time translation invariance, coupled to additional scalar fluctuating degrees of freedom, and you can parameterize the physics in the same way. So you can, in the same way, you can bypass the formulation in terms of models and concentrate on fluctuations. So, what are the signatures of these kind of things? I want to go to the gravitational waves, but just, I mean, it's not obvious that this will give rise to signals. For example, if you consider such oscillation in the primordial cross spectrum, and if you consider the primordial black hole's mass function, actually it is completely smooth. It doesn't see the oscillations because it's a nonlinear effect, and in practice because the abundance of primordial black holes depend on the smoothed density contrast for the experts, and so the oscillations get washed out. So it's rather actually remarkable that a nonlinear effect that I will describe keeps a memory of these oscillations and translate them to omega GW. And so what is this physics? That's now quite mature field, but probably not known still to many people because this has developed a lot recently. We're talking about scalar-induced gravitational waves. The idea is take your primordial fluctuations at the beginning of the radiation era, you know zeta, and because of nonlinear effects, zeta at second order will generate gravitational waves. Okay, usually you think that you basically look for free gravitational waves, box H is 0, but at second order, scalar fluctuations show that. And in practice, when is that source? Is when scalar fluctuations re-enter the horizon after inflation during radiation era. Then you know that the gravitational potential, which was constant on super Hubble scales, starts to oscillate once it enters back into the horizon. During that time, this generates a non-zero source for the gravitational waves, which is efficient, and you can compute that because you know everything. If you give yourself zeta and the statistics of zeta, you know the history afterwards. You can solve for the green function, solve everything, and express. That's a well-known formalism now. Omega GW is a function of k in terms of the primordial cross spectrum. So, but it's a non-linear effect. So it's not like in the CMB large scale structure where it's a linear transfer function times speed zeta. It's actually a convolution, but okay, with a known kernel. What is the amplitude of that? It's 10 to the minus 5 times p zeta squared. So if you consider single filter roll, p zeta is 10 to the minus 9 all the way, and no way, you cannot detect that. But if you consider p zeta of order 10 to the minus 4, let's say, because I explained you that this can happen, and because we have now observational tools to detect that, so I think it's fair to consider this possibility. Then this can be of order 10 to the minus 13 and detectable by LISA. So, in more detail, what is the physics of this is really, remember this, what I was describing, this oscillation in the gravitational potential will give you a phenomenon of resonant amplification. So for simplicity, consider that p zeta is, the cross spectrum is enhanced around some scale k star. It means that the source here in the equation oscillates with a frequency that is basically 2 times, because it's a quadratic, because the second order effect, 2 times the frequency of the oscillation. And the frequency of the oscillation is basically the speed of sound, 1 over square root of 3 in the radiation universe, times k. So you have basically, because of that, a resonant amplification at a specific scale. And that's now well understood. If you look at numbers, for example, if you look at frequencies of the millihertz for LISA, that corresponds to scale that cross the Hubble radius 30 e-folds after the one of the CMB. So really, gravitational waves observatories probe inflation on small scales. And here I quoted Lisa, but you can do the same exercise, of course, for all the different types of probes. Now, this was for a single peak, as most people looked at previously. But I'm motivated for you that the fact that you can have an envelope that is peaked, but with oscillations in it. And basically, I can derive for you quickly how does it work. The idea is that you can model this peak power spectrum with oscillations as a series of peaks, and then put that in the previous equations. And because of that, you can, not surprisingly, one peak will give you the same shape as I was showing you before, with this principal peak. Same thing for the second one, third one, so on. You also have nonlinear effects because now peaks talk to each other, and you can do exactly the same thing as I was telling you. Now you have actually different types of peaks at precise locations, which are related to the locations of the individual peaks. And actually, this very simple analysis enables to predict the locations of the peak, because now, as you can guess, if you look at the envelope of that, of course, because things are superimposed, starting from order 1 oscillation in the power spectrum, that really go from 1 to 0, the oscillations here will be a bit smoothed out, but they will remain. And this we can check numerically. With this simple formula, you can prove that if you have a signal that is periodic in K of this sharp feature, this will also lead to a periodic modulations of omega GW, simply with a different frequency. If you have a resonant feature, as I will show you, this is you also have oscillations that are periodic in log of K, although it's slightly more subtle. You can compute that numerically. Here is 2 different models in 1 and blue, which shares the same envelope, but with different frequency. And here is omega GW computed numerically, and around the principal peak corresponding to, let's say, the one that would correspond to the envelope here, you have superimposed oscillations. And if you actually compare and look at the amplitude of the oscillations, so you look at omega GW compared to the smooth envelope, you have 10%, 15% oscillations. And this is actually a full numerical computations, and it's actually completely fitted by a pure sinusoidal oscillations with a well understood frequency. So what I was describing is take a power spectrum that has a given envelope modulated by something that is a cosine with a periodicity in K. This will give you a scalar-induced background of gravitational waves with an envelope that is determined by the envelope of the power spectrum, and the periodic structures here is inherited by the stochastic gravitational wave background. But because there is this averaging out effect, if you start with order 1 oscillations here, you only get, let's say, 10%, 15% oscillations. And if the frequency increases, as you can imagine, the amplitude decreases as well. Okay, you can. I'll skip the derivation, but you can look at the signatures of resonant feature, and it's actually interesting, but slightly different as well. Now I do the same thing, but start with like motivated by monodromy type of models, power spectrum that is periodic in log of K. Then the resulting omega GW will also have 2 periodic signals, but with a superposition of 2 signals that are periodic in log of K with periodicity omega, the original one of the power spectrum, and 2 omega. I skip the derivation. And then therefore, if you look at the resulting signal, which is the sum of the 2, you will have a complicated structure, because actually the amplitude of these 2 types of signal depends on the frequency. At small frequency, you are dominated by the one with frequency omega, the orange one, and at large frequency, the one with double frequency. And in the middle, you have something weird. So when you add the 2, you end up with such kind of things, where you have at low frequency 1 visible series of peaks, at high frequency 1 visible series of peaks, but with a higher frequency, and in the middle, you have a weird signal, which is just a superposition of 2 things with different frequencies. Okay, so having talked about all these wiggles and features, can ask yourself, okay, but how can is this detectable at all? And basically the answer is yes. So depending on, again, the time of the feature or the scale of the maximum enhancement, you can basically translate these curves wherever you want. As theorist, you have no good reasons to say that your feature is 20, 30, or 40 folds after inflation. So this is the tuning if you want. All right. If you concentrate on Lisa, let's say for the future, are these oscillations detectable? You can get a first idea by comparing with the power law integrated sensitivity curves. You have to actually bin it because it's the typical sensitivity curves assume that the spectrum is smooth, typically a power law, throughout the frequency range. And here it is not at all. So you have to actually bin it. And therefore, because of that, the true sensitivity curves in that case is the green one. And the short answer is that yes, if the signal is sufficiently high so that you can actually see the envelope, there is enough frequency resolution and resolution to actually detect these 10-ish% oscillations of omega GW. And there are ongoing efforts also within LISA to actually show that more concretely. Let me again really emphasize the potential of discovery of that. We're saying that if we're lucky, we may detect this type of oscillatory features in which have no other source at least to the best of my knowledge for the moment, and quite model independently, the periodicity here of the signal, quite model independently, will tell you that there has been a sharp feature during inflation, whatever it is exactly, and remember, because there is this link between the frequency in omega GW is related to the frequency of the power spectrum, and this one is related to the time of the feature, the scale of the feature, you deduce when was this thing happening during inflation, which would be, of course, a terrific discovery. If you go into more model-dependent things, you can also deduce the duration of the feature or the energy scale, but this is the one that is more model-independent. Okay, I'll explain two additional things. I stress this dark ages of inflation, but we also don't know much about the other subsequent dark age, which is what is the expansion history between the end of inflation and BBN. And there are lots of reasons to consider non-standard expansion history, because actually the standard one is just postulated. Radiation, so usually the standard history is after inflation, a short phase of reheating, and radiation domination throughout and until you reach BBN. But it may not be the case, and we studied that under a few assumptions, and under the assumption that the equation of state is constant around the relevant time, and with different also propagation speed of scalar fluctuations. So the typical setup that I was showing to you before corresponds to a perfect fluid radiation with W equals C squared equal 1/3, but we look at different combinations. And the main results are, at least I concentrate on the perfect fluid case, that all the previous templates hold. All the previous templates of resonant and sharp feature, they are processed in the same way. There are, however, differences between resonant and sharp features. For resonant features, the frequencies of the oscillations, these two oscillatory signals with frequency omega and 2 omega, are not affected by the equation of state, but the relative amplitudes are, so that you can extract the physics both of inflation and of the expansion history out of that. Don't give too much details, but that's a short summary. For sharp feature, it's more subtle because actually remember that since the beginning, the frequency of omega GW is related to the one of the scalar per spectrum by this factor square root of 3. But square root of 3 was not just a number, it was actually W, or the speed of sound, W to the power minus 1/2. So when scalar fluctuations re-enter the Hubble radius in a period which is not radiation domination, but dominated by a fluid with equation of state W, in general, because you just observe that, you don't know whether there was a feature with this given frequency in the scalar pro spectrum, or what comes from, let's say, a non-standard equation of state in general. But actually, this degeneracy can be broken because if you increase W, if you have stiffer equation of state, the amplitude of the oscillations get larger. And you can show in that way that the relative amplitude of the oscillations, which cannot be greater than, let's say, 15% in the case of radiation domination. Remember that even if you start with order 1 oscillation in the primordial Probe spectrum, and you cannot be larger, this is processed into only 15% modulations. But this was for radiation domination. So if we ever detect these modulations with an amplitude that is greater than these 15–20%, this will be an indication of two very strong things, which is new physics during inflation, these sharp features, and after inflation, in the sense that it was not radiation domination all the way. Let me just finish with one piece of information. One last thing. Here what I describe is if you have enhanced primordial fluctuations on small scales, model independently, you can compute these scalar-induced gravitational waves and learn things about the scalar Probe spectrum that you basically don't know otherwise. Okay, very good. But there has to be mechanisms, physical mechanisms of different types that give rise to these enhanced primordial fluctuations. And these physical mechanisms also, in general, source gravitational waves during inflation. And this add a signal. And so in a paper soon to be released, we actually showed very generic results for scalar fluctuations that are in an excited state. In the case like for the sharp features. Remember the sharp features, you start with something that is in Bunch-Davis, you have a phenomenon, a sharp feature during inflation, and then an excited state is generated. This is what I'm going to explain here is more generic. This is for any excited state after some time. Sharp features being a particular case of them, with remember the specific link between Bogoliubov coefficient that was giving rise to these oscillations. But what I will describe below is just depends on excited states, not which can be generated in many, many different ways. In practice, what we're talking about is computing the one loop tensor per spectrum generated by the scalar fields active during inflation, right? Two scalar degrees of freedom during inflation source gravitational waves, and you compute the 2-point function of this inflationary era generated gravitational waves. So if the scalars were in vacuum, this would be very small. This would be of order h over the Planck mass to the 4, and which means that remember that the gravitational waves generated after inflation, they were proportional to the power spectrum p zeta squared. But now it's actually even suppressed by epsilon, because actually the source of the source of the anisotropic stress tensor is not zeta itself, but it's really the scalar field fluctuations, and the scalar field fluctuations are related to zeta with this factor epsilon. So in the vacuum state, that would be very small. But if you have excited state, you have interferences, constructive interferences between positive and negative frequency modes. So people who know maybe non-Gaussianities know that typically in non-Gaussianities with excited states, you can have this type of interferences. And here you can see somehow, I mean, you can smell that the Probe spectrum here is related to the kind of the tensor scalar non-Gaussianity squared, and in the same way as excited states amplify non-Gaussianity, they amplify here the signal of the gravitational waves generated during inflation. And here is basically, so compared to an order one, compared to the naive value, you can have an enhancement by several orders of magnitude and order one oscillations. And I just want to write that here. That's basically my last slide. So I'm considering, again, excited state that are dynamically generated and that are valid after some time during inflation. And again, some time corresponds to some scale during inflation. There was an in region and there is an out region in which there is excited state. And the thing that I was telling you before was this kind of things, this green curve. So there are two scales here. The scale corresponding to the time at which the excited state becomes operant, and the scale k star, which is where is the maximum of the scalar power spectrum. By definition of excited states, this scale should be deep inside the Hubble radius at the time of the existence of the beginning of the excited state. So it's related to this scale k out by a large factor gamma. And now, when you have an excited state like that, we've shown that the signal can be very large and have these order 1 oscillations, not anymore these 10-ish% oscillations, but this very large wiggles here. And actually, if you compare the maximum value here to the maximum value of the post-inflationary era gravitational waves, this grows a lot with this large parameter gamma, which quantifies the excited state to the power 5. So it's suppressed naively by epsilon squared, but boosted by that. It's also amplified by the number of fields and during inflation. That's something rather useful to keep in mind. I mean, these scalar-induced gravitational waves generated after inflation, they probe what has been generated after inflation. So basically it's zeta. But the one generated during inflation, they probe what was active, what has basically a stress energy tensor during inflation. And it may, if there was multiple degrees of freedom feeding zeta, you will not see the difference when you just observe zeta at the end. You don't know how it has been created. But if you observe the one generated during inflation, you have extra information, and that's quite visible here. And we have analytical templates, actually that corresponds to this gray line here. We have simple analytical templates with this order 1 oscillation that matches. Okay, so let me conclude. What I wanted to explain was, well, one, primordial features are motivated target of new physics. This has been known for a long time and studied a lot for usual probes, CMB, large-scale structure. On small scales, inflation can be drastically different from slow-roll vanilla models. And actually, you can even argue that this is natural. And I've shown that a large peak from a localized event necessarily comes with order 1 oscillations. So the feature is not a small addition, it's actually an entire part of the signal. These oscillatory features in general are transferred to the frequency profile of this scalar-induced gravitational wave background. This works for sharp and resonant features, although in different ways. That's quite model independent. In addition to that, when you consider gravitational waves generated during inflation, if the inflationary degrees of freedom were dynamically put in an excited state, this will also boost the primordial gravitational waves with now very big order 1 oscillations that are even more easily detectable. So all that opens new windows on these dark ages of inflation, which we don't have access otherwise. Also on the dark ages afterwards, this expansion history. And all that I think motivates further works, both on the theoretical control, because as I've told you, in the type of models we've considered, let's say, derived tentative bounds for back reaction and perturbative control. Typically in this kind of studies, this is not often done, but this is very important. I mean, you don't want to motivate things and templates for Lisa if you just put something behind. You want to be sure that your models are robust. So theoretical control is quite important, and this also motivates specific works for detecting these kind of wiggles, let's say in Lisa and with other probes. So I conclude here. Thank you for your attention.
Any more questions?
So kind of related to the one of the last comments you made. So you mentioned earlier that you focus on like beta over alpha of order 1.
Sorry, say it again.
So you focused earlier on beta over alpha of order 1, so like significant particle production.
Yes.
So I was wondering about whether that efficient particle production back reacts on the inflationary dynamics. Like, does it mess with the homogeneous expansion?
Yes. No, indeed. So as I stressed, that's why I was stressing this theoretical control. If you just you have to take that into account. For example, so these excited states corresponds to have some non-zero energy. And in the computation, at least that we have done, I mean, it's not a problem that things back react on the background. If they back react, you just have to take it into account. That's not what we have done in our precise setup. So it means that there is some bound. But let's say in axion gauge field, I mean, the types of models that I have flashed, they have a transient tachyonic instability that boost fluctuations. And this type of things are not at all far-fetched. The paradigmatic example of axion gauge field inflation corresponds to a transient amplification, in that case of gauge field. And it's known in that case that you also have to be careful with back reaction. And if there is some back reaction, just take it into account. So that's for back reaction. And perturbativity in the same way. You cannot consider, for example, an infinitely sharp feature. This will excite high energy modes, and there are bounds on that. So we took that into account, and that's formulated basically in this bound. So that limits the efficiency. In that way, actually, the two type of things that I've described, I mean, I've mostly concentrated on this scalar-induced gravitational waves generated after inflation that basically just reprocessed what was the primordial density fluctuations. And this is this is constrained because of this mechanism, because this is constrained by itself, the maximum amplitude of the primordial cross spectrum. Because the physics is different, the ones generated during inflation are actually much less constrained. But yes, in general, you do have to take that into account. And I mean, I see this bunch of works as, wow, surprisingly, features that has been extensively studied on large scales. Our first work showed that they can lead to features in omega GW. And if you look at what people look for, you know, in LISA and so on, they beat some pipelines. For the moment, they were looking at smooth curves, at smooth omega GW. So the mere fact that this can exist, I think this is interesting. But of course, once you have done this first work, you have to refine things to check, okay, how much this can be realistically generated, what are the constraints, and so on. So this motivates further work.
In your definition of localized feature, you would not include these near inflection points, right? Because these would generate a peak, but no oscillations in it.
Right. Near inflection point is typically would correspond to an enhancement of the cross spectrum that is not localized, but that is broad. Mm-hmm. So if you want to remember so typically this inflection point type of stuff had been considered as models to generate precisely a boost of the cross spectrum on some scales with the idea of generating afterwards PBH. Yeah. And in that case, it will be this. But you see, this is actually not sharp. This is actually, you see, in that just toy example, 20 orders of 20 E-folds, and that's typically what's going on because it's related to the duration of this phase. What I have in mind is most things that are this was really cartoonish. Is if you look at the real plots, corresponds to things that are amplified very sharply in one or two, corresponding to one or two E-folds.
Thank you.
Any more questions? Maybe going back to the very original one, do you have any potential that you can show us? Even just one random example is okay.
I don't have slides about that, although I can open papers. Well, if you want, I can show you. Let me see. Okay. Sorry. Okay, I go there. I wanted to spare you the details of the model building and sometimes. Okay, So if you want to see the technicalities, okay, you can actually see. So let me check where to start. Okay, quite generically, in a model independent manner, if you look at the quadratic action for fluctuations, if it was single field, it will be this, right? The action for zeta, massless zeta, that's it. If you have additional degree of freedom, they will have their own, if you want, action with a given mass, because now the other degree of freedom is not conserved, I mean, it's not massless, and they would be coupled. Typically, they are derivatively coupled, zeta dot q, and in concrete models, nonlinear sigma models, there is this important parameter that I was mentioning, the perpendicular acceleration that was described here. So you consider, let me go here, okay. You consider, okay, nonlinear sigma models with several degrees of freedom. You look at the fluctuations and, okay, this parameter quantifies the rate of turn of the trajectory. If it is a straight line or geodesic in field space, this acceleration is 0, and basically it's as if it's a single field model, simply embedded in a multi-field space. If it is non-zero, it does two things. It couples the additional degree of freedom to zeta. That's what makes it actually multi-field. And it also does something, which is it creates a negative contribution, which can be very large, to the mass of this entropic degree of freedom. And that has quite a physical interpretation. That's basically the centrifugal force of the bobsleigh effect. If you have a turn, you will be displaced from the minimum, and you will tend to go up in the hill here when you turn. That corresponds to a negative contribution to the mass, and this can be very important and generates tachyonic instability. Okay, I don't know if that's enough. Then I can give you more technical details if you want afterwards about how we can parameterize that. But that's the type of thing that
we can look at it later. But thanks, yeah, that was helpful. Sure. Anyone else? All right. So if there are no more questions, let's thank Sebastien again.